So the second example that we're doing for uniform plane waves explains why E and H are perpendicular to the direction of propagation for these plane waves. So why are E and H perpendicular to the direction of propagation? I'm going to start writing k as a vector, meaning it has magnitude, the wave number k, and it points in some direction that is the direction of propagation. So to do that, I'm going to do an example. And I'm going to assume an electric field that has some amplitude that we don't really care about, some vector, some polarization vector that is general. It could be in any direction, and it could have a component that is along the direction of propagation, because I'm about to show that it doesn't. And then it's got, I'm going to assume that it's propagating in the z direction, but really it could be any direction. It's just easiest to deal with this way. So the next thing I'm going to do is find the magnetic field due to this electric field using Faraday's law. And that is that the curl of the electric field is equal to minus j omega mu h. Okay, so far so good. Divide through by minus j omega mu, and we can find out what the magnetic field is over here. So if we write down what the expression is for curl, and now I always have to write this out as the matrix determinant method, so I do x hat, y hat, z hat, derivative with respect to x, with respect to y, with respect to z, and then I've got ex, ey, ez here at the bottom, and I'm taking the determinant of this matrix, so then the curl works out to be partial ez, partial y minus partial ey, partial z in the x hat direction, plus partial ex, partial z minus partial ez, partial, whoops, that's not an x, partial x, and that's in the y direction. And then lastly, we've got partial ey, partial x minus partial ex, partial y, in the z direction. All right, so that's our curl. Now let's take a look at this though. We've said that this is a uniform plane wave. Uniform plane wave. Meaning that E and H only vary along the direction of propagation. In this case, that's z, but it doesn't always have to be z. But in this case, it is z, and that makes our job really easy here, because anything that is not a z derivative goes to 0. So these x derivatives go to 0. These y derivatives go to 0. Whoops, I didn't mean to erase it, but whatever, it's 0 anyway. The only terms that are left are x and y. You can see that here there's no z component at all. Meaning that the magnetic field here must be perpendicular to our propagation vector. And if you did the same thing using Ampere's law to start with instead of Faraday's law, you would get that the electric field is also perpendicular to the propagation vector. So that's our second example.